Let's talk about transformations of functions and graphs. This is an essential element because we have a few library functions that we understand, we know how to graph, we're getting good practice with, but we want to build that out and show some tools to build much, much more general functions and understand how they work and what their graphs are based on the library functions. So it's not going to create anything particularly new in terms of algebra that we haven't seen, but we're going to be able to graph them and understand the why of how simple graphs get modified to become a little more complicated. So we're going to start with a very familiar library function, f of x equals x squared. Super simple algebra, and we've been getting more familiar with the graph, which is a let's call it a parabola. And I'm going to go back and forth between algebra and the tabular presentation and graphs, because that's really essential. If we had never seen this function before, we would just plug in a few simple points, the simple x values. We'd take their squares to get the y values. And of course, we'd get a graph that's this nice, pleasing curve. So let's see what happens if we modify that in a pretty simple way. We're going to take that f of x, and we're just going to add 2 to it. So this is a very, very special case of adding 2 functions, but importantly, we're just adding a constant. And so that's just y equals x squared plus 2. Not algebra that's ridiculously new at all. It's something we're very familiar with. But what is that graph going to look like, and how does it relate to the graph of y equals x squared? Well, I think it's helpful to do the table first. And if we look at the table, we're going to put in, let's say, put in the same x values. And we'll see that that's not a given. You don't necessarily want to put in the same x values every time. But here it's totally going to work. So we take minus 3, we square it, we get 9, and then we just add 2 to the 9 that we had. Minus 2 squared is 4, plus 2 is 6. So these numbers are just exactly what we had in the previous table, just adding 2. That's exactly what this says. It says take the outputs of the original function we had and add 2 to all of those outputs. So let's see what the graph looks like. So for example, 0 doesn't go to 0 anymore, it goes to 2. 1 doesn't go to 1, it goes to 3. 2 goes to 6, 3 goes to 11. Similarly for the negative numbers over here. And if we pick any value, like minus 2, which used to go to 4, notice what's happened. If I was about to plot that, like I forgot the plus 2, I was just about to put a dot there, I could easily fix myself. And somebody could say, wait, you forgot the plus 2. Do I have to go back to the drawing board? No. I just add 2. And if I take the same x value and I add 2 to the y value I was going to plot, which was 4, that just moves it up by 2 units. And so that's what happens to the entire graph. So this is probably the simplest transformation to understand, that we're going to have something where I was ready to graph the output, and then I just add 2 at the end, and that just shifts every single point up by 2, therefore it shifts the graph up by 2. So this is what we would call a vertical shift. And what's simple about it is that because it was kind of on the outside, the square function had been accomplished already, and then I add the 2 as the last thing, then it's just going to be a simple vertical shift. So let's go over to a Desmos graph here. And so I've got f of x equals x squared here. Let's activate f of x plus 2. Okay, that's groovy. And this is really, Desmos is really nice because I can animate this process. What I'm going to do is I'm going to call this K, and I've actually activated a slider here. I don't need that. And by making this a letter and making a slider, I can make this dynamic. So this really, I think, makes it pop more. That if I take that same base function, it's always based on f of x equals x squared, and then I'm adding that k. Notice how I'm writing this. I'm saying, let's just do f of x. Let's get that output number, and then as a last afterthought almost, the last thing we add k, it just takes every point either up by a positive number, or of course, if I add a negative number, that's going to decrease those values. So for example here, minus 2 squared was going to be 4, and I subtract about 2 from it, and I'm down to 2. So that is a nice picture of what that does. So here I was relying on the fact a little bit that this was a very familiar function, but I've created one with kind of a weirder function. Let's not worry about the formula I used. Let's just graph this funkier function, okay? And now what happens if I subtract 1 from that? The same principle applies. I don't need to know anything about the formula that produced this function. I don't need to know any particular special values. I don't need to have a table that's particularly precise or anything. I just know that whatever this function did, so g of minus 1 looks like just a little bit under 1 there. And it's a little bit to the right. It's on the downslope after the sharp corner. And if I subtract 1, oh, actually, that's right, that's 2 there. The vertical scale is kind of not showing. I'm not sure why. If I take g of x and I subtract 1, it's just going to take that point down. It's going to take that point down, that point down. The 0 goes to just a minus 1. Everything just goes down. And if I put it on the slider, then it'll animate in the same way. So when I've got an add or subtract outside the function, then I'm going to be doing a vertical shift. Okay, let's go back to this one. Okay, so how would we do a horizontal shift? So the vertical variable is y. We graph the y, the output, vertically, and that's why when we affected the output directly, it was a vertical shift. So the horizontal variable is the input. That's x. So it seems like it might make a horizontal shift if we directly modify the input of the function. So let's go back to f of x equals x squared, and let's see what happens if instead of putting plus 2 on the outside, I put it on the inside. Notice these are both compositions of functions. That's another way to say this. This is composing the function f with a very simple function that just changes x into x plus 2. So this relates to the composition story, but it's very special. So that's just going to be x plus 2 quantity squared. Again, the algebra we're absolutely familiar with. So it makes sense to want to graph this kind of function. Well, the guess, so I want you to guess here what that's going to do. And I'm going to have you record your guess. And let's look at the graph first this time. So there's y equals x squared. That's f of x, our original function. And most people guess, if they guess that it's going to be a horizontal shift, that's correct. But most people think, well, plus 2 seems that should go to the right, because isn't the number line, the right-hand side of the number line is plus, the left-hand side of the number line is minus. But in fact, it shifts left. And let's investigate that a little bit. It's because we were modifying the input, but let's just work it through. And this is where the table is very useful. Okay, so let's look at the table. So minus 3, what did I do? I added 2 first, right? Remember what this function is, x plus 2 squared. Let's bring it down, right? Let's hide this for a little bit. So we look at x plus 2 squared, and I take minus 3, I add 2, I get minus 1, and I square it, and I get 1. I take minus 2, I add 2 to that, I get 0. Square that, I get 0. Okay. Way over here, like 3 plus 2 squared, I get 25. Okay, so hopefully you believe that it really is correct. That, for example, minus 2, I added 2 to it. Now it's 0. And I square it, and I get 0. That's this bottom part. That's called the vertex of the parabola. And that clearly corresponds to this over here. So it is really being shifted 2 to the left. And we can understand that better if we look. Let me bring this table back up. Let's actually put in a row for the first thing we did. It was a two-stage process here. We took x, we modified x by adding 2 to it, and then we created y is x plus 2 squared. We actually did the interesting part of the function to it. Okay, and so what's going on here? A really useful thing is to actually not so much going from inputs to outputs, but ask, for example, let's see, to figure out where this vertex went, this bottom point, I want to ask not so much what happens when I put in a particular input. I want to say, okay, if I think it's a horizontal shift in any direction, left or right, I think there's going to be a point where it touches the axis, where it has value 0. So we're going to ask, what should I put in as an input to get output height 0? And this graph seems to suggest that needs to be minus 2. Well, that makes perfect sense, because if I want to get output 0, well, that means I want the thing that I'm squaring to be 0, and I have to fake it out. This is where the way I like to say it. I like to say that we have to fake this thing out. The square function, if I want the square function to output a 0, I need the square function to see a 0. But if that is the input plus 2, I have to undo that. I have to anticipate and undo the plus 2 in x. So to get that vertex, to get that bottom point, the y equals 0, I purposely put in a minus 2. So I can think of it as sort of cleverly changing my input. Then the +2 cancels. I get the 0, and I get the 0 out. Let's try that with another point, for example. Suppose I want to figure out, I know that there's this point over on the right-hand side of the original curve where that had height 4. And to figure out the shift, I say, well, where on the new curve am I going to get height 4? Well, this seems to say that that should be x equals 0. Well, that's exactly right. Because if I want to get height 4 on the modified curve, then the thing that I need to square, which is x plus 2, had better be 2. And so I need to anticipate, like, wait a minute, I'm already going to add 2. I do not want to put in 2 or 4 into here. I want to anticipate and undo the +2. I want to put something that's smaller. I want to put 0 in. Then the x plus 2 is 2, and the x plus 2 squared is 4. So the fact is that when you are modifying, when we modify the input, things, they admittedly go backwards from most intuition, but we can figure it out. Think of it as needing to, again, anticipate and undo. I like to say fake it out. Fake out. Well, undo the change that we're making. Like that +2, we actually anticipated and undid it by putting in numbers that were too smaller than we expected to get the same outputs. And the way I say that, I guess, I don't know if it makes sense to anybody but me, we sort of fake out the function. We think about the square as that last thing that happens, and we want to engineer, by putting in the correct x, we want to engineer that what that squaring function sees, which is not x, but x plus 2, is exactly what we want. And to do that, we actually ended up having to subtract 2 from the values. So that's a few of the transformations. We'll talk about more of those transformations in class, but that's the shifts. Let's just go, I don't want to make this too long, but let's go ahead and try this. Usually, H is the letter that's usually used for transformations here. And so notice if I add like a 2 inside the G function, notice I've shifted that to the left. And the bigger an H I add, so this would be like G of x plus 4, I've shifted it 4 units to the left. If I add a negative, that's how I shift it to the right. Similarly, if I look at the parabola, oops, sorry, okay. Woo. Let's just clean it up a little bit. Then I look at the parabola, and again, if H is positive, I shift to the left, and H is negative, I shift it to the right. Okay, that's a good place to stop.